Hello everyone. In this video I'm going to be talking about a statistical test known as Spearman's rank, or Spearman's rank correlation coefficient as it's sometimes called. Now, statistics is incredibly useful in a variety of aspects in biology, chemistry and physics. Now, the presence or indeed the absence of a correlation between variables can be determined using something like this. Now, it's important to remember that the presence of a correlation does not always mean that two variables are related or connected. I mean, if we just take, for example, the number of falcons in Britain in the 70s, as that went up, the number of British people going abroad for their holidays went up. Now, both increase, but neither, I'm sure you'd agree, have any connection between one another. Whereas Spearman's rank correlation does look for a connection between two things. It sees if, as one thing goes up or increases, if something else goes up, or as one thing goes up if one thing comes down. Now, what you can do is, if you have a set of data, you can draw what's called a scatter graph. I'm just going to draw a rough version of one. You get points on a scatter graph that looks like this. So you don't do a line of best fit. You just have the points marked by x's, for example. Now we have one variable on the bottom and one up the side, so one on the x and one on the y-axis. Notice there is no real independent variable and dependent variable in this case. We're looking at how two separate variables relate to one another. We're looking for that correlation between them. Now, if you draw a scatter graph of data and the points appear to just either show some random grouping like this, or if all the points are a U-shape or all squashed together, you wouldn't really use this test. But if the points appear to show an approximately straight line, then you can use a Spearman rank. So if instead of what I've just drawn you had something like this, or even something like that. Something where there appears to be some kind of link between the two variables they're looking at. So we're going to use something called Spearman's rank correlation. Now, for this, we're going to have an example, and our example is going to be related to, we'll just think about, I'm just going to draw a random, perhaps not a very good picture here. We're going to think about some broad beans. So I've just got a rough sketch of some broad beans here. Just for completeness sake, we'll draw in a little piece there. So we've got some beans, and what we're going to do is imagine in some practical, in the classroom, we're going to look to see if there's a correlation between the length and the mass of broad beans. So it's been suggested that the length and the mass of these beans are related somehow. So we're going to do a Spearman's rank to see if that is indeed the case. So the first thing we're going to need is a set of data to look at. So we'll just move this up here. We're going to have a little table, so recording the mass here, and let's have the length in centimetres over here. So we're going to need certain values now. So let's say for a mass we have 0.7, 1.2, 0.9. I'm just making up some random numbers here. 4, 1.2, 1.1, 1.0. Shrink this down a little bit more. And let's go for 0.9, 1.0, 0.8. So let's say we've worked out the mass of 10 of these beans. And in grams, we've got the values down the side. And now we're going to record the lengths. in order. So again, we'll just make up some numbers here. 1.7, 2.2, let's say 2.0, 2.3, let's have another 2.4, let's have a 2.2 again, 2.0, 1.9, 2.1, and finish on 1.6. Just a random example here of a set of data. So we've recorded the mass of 10 beans and the length of those 10 beans. Now what we need to do is, for Spearman's rank the actual data. We need to rank the mass column and the length column in order from smallest to largest. So this is the next stage. We're going to have here, let's put in another column called R. Now R is going to represent, let's do an arrow from this column, our rank 1, our first rank. So for Spearman's rank, what we have to do is rank the data in order of size. So we have our number 1, our first rank, as the smallest number, which in this pile, or for the mass, would be 0.7. So that's the first rank. Then their second rank would be the next biggest number. So it's down here at 0.8. It's 2. Now if you notice, we actually have a 0.9 and a 0.9. We have two numbers that are the same. So if that happens, then we think of what the ranks would be for the next two. So that would be a third and a fourth rank, so 3 and 4. And we find the average of those numbers. So we say 3 plus 4 is 7. Divided by 2 to get the average, that would be 3.5. So we actually give both of those a rank of 3.5. Now, because we technically have used our third and fourth rank up on those two numbers, the next one in the list would be our fifth rank. So we look for our next largest mass and we give that the rank number 5. Now, we've got here 1.0 and 1.0. So again, we're going to need to do an average of two ranks. So if we're looking at rank 5 and 6, the average of 5 and 6 is 5.5. So this would rank in at 5.5. This one would also be 5.5. So then our next one logically would be 7. So that is a rank of 7. Then we have a rank of, and we need to do the same here. We've got 2. So this would be 8.5 and 8.5 because the next two ranks would be 8 and 9. So we find the average and give them both the next two largest masses a joint rank of 8.5. And then finally, this one would be 10 because we've used rank 9 on the previous two numbers. Now I've picked numbers deliberately to show you how to do average of ranks. So that's why we've got an 8.5, a 3.5, a 5.5. Certain data sets you may not need to do that at all, but in this one you do, and I've shown it again deliberately to show how it's done. Now we're going to need to do rank 2. This time we're going to need to rank all of our lengths. Now if we do the same, this would be our first rank because this is the smallest length. We've got our second smallest length up here, that's number 2. We've got number 3 here. Then we've got 2 with 2 numbers, so this would be a 4.5. And this one here would be 4.5. Because we've got two lengths both at 2 centimetres long. So we find the equivalent rank 4.5, 4.5. So the next rank would be 6 down here. So we've got 6. We've got a 7.5 and a 7.5 rank there. Because one rank would be 7, one would be 8, so we find the average. So logically the next number would be 9, and that would be 10 there. Now, the next stage is to find the difference between the two ranks. Now, there is a formula for Spearman's rank correlation, and we will be coming on to that. I'm just going to lay out the table as to how you would do this if you were doing this particular statistical test. We'll get all the numbers and then I'll show you the formula and explain, it will be clear then why we've done these particular columns. So we're going to move over here. Now we're going to look for D, which is the difference in ranks. So this is the difference in the ranks, our D column. Now it doesn't matter if it's negative here, so you just do rank 1, essentially minus rank 2. So we'll get a -1, get a 1 and a -1. We'll have a 1, a -1.5, a -0.5, 1, 0.5, -0.5 and 1. So these are our D values. What we've done is do rank 1 minus rank 2 to give us these D values. Now what we want is D squared. We're going to square each of these values. So those values of D that we got between the difference of rank, we're going to square them all and we'll get rid of those negative numbers. So if we do, we'll end up with 1, 1, 1, another 1 there, 2.25, 0.25, 1, 0.25, another 0.25, and a value of 1. If we added up all of the values for D, so the sum of D, what that value would come out as is 0. And if we wanted the sum of D squared, that value would come out at 9. So now I'm going to explain why we've done all of those rankings and differences. So for this, we're going to shrink the screen just one more time. Move it up to here. Now the formula for Spearman's rank, to work out that correlation coefficient, so R, it's equal to 1 big 1 minus 6 times the sum of D squared all divided by N squared minus 1 in the brackets all times by N. Now sometimes that gets multiplied out as N cubed minus N. That's saying the same thing. So N squared minus 1 in the brackets times by N is the same as N cubed minus N. All they've done in that is just multiply out the brackets. And all of this is treated as one separate entity. So now if we follow through and use our numbers from the table, you'll get 1 minus, and that'll be 6 lots of sum of D squared, which is 9, divided by, and remember all this is in one big thing, 10 squared minus 1 times 10. And if you do that number, so n squared, n being the number of pairs of measurements, that would come out at 990. So R, if we just go back to our original, R is our rank coefficient. D squared is the difference in ranks. So this D squared here is the D squared I've just highlighted there. And N in this case is the number of pairs of measurements. And usually, if we have at least 6 pairs, we can get a really good set of data. And in this, we've got 10. We've got 10 lots of masses and lengths. So if we go back to our formula, if we work all of this out, so if we did 1 minus 6 lots of 9 divided by 990, that would come out as a value of R at 0.945. Now you're probably thinking at this point, that's a random number, it means nothing. But it's very telling. The correlation coefficient can be any value between 1 and -1. So we've got a number here of 0.945. It can go from 1 all the way to -1, this number. Now if it's 1, that means there is a strong positive correlation between the two sets of data. So a value of 1 indicates a perfect positive correlation, whereas a -1 indicates a strong negative correlation. So positive being that as 1 increases, so does another. Negative means that as 1 increases, the other decreases, does the opposite. And a value of 0 means there's no correlation at all. Now, in an exam, they would give you a statistical booklet which has in it a table showing what's called degrees of freedom. And we use that table, as in other statistical tests, to look at the 5% probability. Because what we want to say is that we want to be 95% or more certain that the result that we have is not due to chance, and that it is statistically significant. That correlation isn't just due to chance, there is a statistically significant reason why we have it. Now, I'm not going to draw out an entire table of degrees of freedom, but I will just, in this example, draw a small portion of it to make one point. So in terms of degrees of freedom, in this example, in this stats test, it's recorded as the number of pairs of measurements we have. And then what we have is something called the critical value. Now, you don't need to learn these off by heart at all. Though you would get given this in an exam setting, this particular table. So we have values like 6, 7, 8, 9, 10 pairs, and the critical value could be 0.886. It's very specific. For 7, 0.786, 8, 0.783, 9, 0.683, and for 10, 0.648. Now this is why this table is important. We obtained a value for R of 0.945. So to be 95% certain that that result is significant, you look at the critical value on the table that's provided for the certain number of pairs that you used and see if you're above or below that critical value. If you are above, then it's significant. So at 10 pairs, because that's what we had, 10 pairs of set of data, the critical value is 0.648. Now our value of 0.945 is massively over the critical value. So as 0.945 is greater than 0.648, we accept that there is a significant correlation between the mass of the bean and the length of the bean. We can be statistically sure that the length of the bean does relate to the mass of it. And that's what Spearman's rank correlation shows. If there is a link between two different variables. So what we have here in this video is the formula for standard deviation, Spearman's rank, in which you need to work out D, the difference between the ranks that you assign two sets of data, and D squared, and N, the number of pairs of measurements. You come out with a value for R, the rank coefficient. You see whether it's either towards 1 or -1, the positive or negative end. And then you use that number and compare it against the critical value on a table provided to see if you can accept that there is a significant statistical reason as to why you got the result. So in this example, because we got 0.945, it would suggest that our data very much looks like this, a perfect positive correlation. Okay, hope all that helps.